talk. So this is a scalable version document store in PostgreSQL. If this is not the talk you wanted to see, you're in the wrong hall. The other talks are, I guess, upstairs. My name's Art Gillespie. I'm a software engineer at a company called Udacity, which I'll talk a little bit more about in a minute. You can find me on the internet if you're into that sort of thing. I try to keep the brand consistent. I don't have any clever names. That's me on GitHub and Twitter and everywhere else. After going to a couple of sessions this morning and talking to people at lunch, I feel it's really important to call this out. I am not a DBA. I'm a software engineer that builds apps, and you're not going to get any deep insights into the internals of PostgreSQL from me. I'd love to get some deep insights about the internals of PostgreSQL from you all. So I know this was listed as an intermediate talk. I just wanted to call that out in case anybody wants to run for the door. So I work at a company called Udacity. Has anybody here heard of Udacity? Anybody taking classes with us? All right, well, close enough. So Udacity is an online learning platform. We tend to focus on sort of bleeding edge technology. We have a lot of machine learning courses and nano degrees. We have a lot of sort of VR, blockchain, those sorts of things, autonomous cars. And what we do is we partner with industry to figure out where the sort of shortcomings are in these technical skills. And then we build curriculum to sort of develop these skills in either existing engineers or in people that are making career changes. Sure. This is all my fault for not wearing a collared shirt, right? We're good? Y'all hear me? All right, cool. And so we have a bunch of courses, and we're going to get into some depth about this, not to pitch the company, but because the problems that I confronted at Udacity were related to sort of the development of this content and the delivery of it. So today we're going to talk about three things: why we sort of found ourselves in the position to build a content store on top of PostgreSQL twice in the last 3 years, the design that we use to implement it, and some stuff which are kind of things that surprised us that we learned working with PostgreSQL, good things that I thought I would share. And before we get started, it seems like this is a pretty casual conference, but I just always like to call out, feel free to just raise your hand, start talking, whatever. I like an interactive audience, although after lunch that may be a bit too much to ask for. Cool. So why did we do this? Why did we build a document store? Well, we have a lot of content. But it changed over time. You'll see in the abstract that we started on Google Cloud Data Store because we were a Google App Engine shop. And that was really, in 2012, that was really your only option for storage if you were on App Engine, was to use Google Cloud Data Store. This predates Cloud SQL. And in 2015, when I joined, there were 15 engineers, one big App Engine app, about 30 GitHub repos, but most of those were actually related to the sort of things that we would get students started on programming, not our actual code. We really only had 2 repos that mattered for engineering. And we had 0 PostgreSQL clusters. And we had 0 DBAs. So fast forward to today, we have 103 engineers, 330 microservices, 1,382 GitHub repos. I didn't go and figure out what all those were, but that seems a little high. And 144 PostgreSQL clusters. So we literally have 1.4 PostgreSQL instances for every engineer. And we still have 0 DBAs. These numbers, before I joined Udacity, if I saw these numbers about a company, I would think it was insane. 3 microservices per engineer, 1.4 databases per engineer. All I can say is that it works really well for us. If you want to spin up a new microservice and a database and Redis instance, I should have put the number of Redis instances, it's pretty high as well. You just push a button, and you've got all the resources provisioned for you. And for us, even though there's a fair amount of chaos involved, the velocity that it gives us and the sort of innovation that our engineers are able to bring to bear on problems that we confront is worth it. So we need to talk about the content structure at Udacity. The easiest way to do that is sort of just take a quick dive through the front end. And so content at Udacity is basically broken down like this. You have a top-level program, which you see in the upper left-hand corner here. And that'll be like a nano degree or a course. Programs have parts, which you see down the left side navigation. Parts have lessons, which in this view is the sort of main view here. You'll see have the first lesson and the second lesson. If you go into the lesson viewer, you'll see concepts down the left side. And in the main area here, each concept has atoms. And you can have, for example, here, this is a programming atom. You can type Python in, and it goes back to server, gets evaluated, and comes back. You can have sort of text and image atoms. And you can have video atoms. And this is actually our most common kind of atom. This is my favorite video atom because I'm in it. And the title of this concept is Why Art Should Have Documented His Code. It's a real page turner. So programs have parts. Parts have lessons. Lessons have concepts. And concepts have atoms. I'm thinking of a data structure. This is my after lunch magic trick. I'm thinking of a data structure. Can anybody guess what it is? It's doing good. Maybe more generalized. The answer was file system. Going once? It's a tree. And so our content maps, like a lot of content, into a pretty neat hierarchical tree. And in fact, the exact nature of this tree has changed over time as we've sort of evolved. But generally, it's always been a tree. And so, this is the squeaking. I keep thinking I'm hearing people ask me questions. And also, trees are usually, they really should be upside down. So when we store the tree, back in the good old days in Google Data Store, we would just generalize every piece of content as a node in the tree. And every node has a unique identifier and a semantic type, which gives you sort of a polymorphic way for kind of application domain concerns to figure out what kind of node it is. Is it a part? Is it a degree? And then we referenced the children nodes in a field called children, an array of strings that refer to other keys. And so this is a pretty straightforward way to map a tree, especially in a NoSQL store like a data store. And so it might look like this. Does this make sense? Does anybody not grok this? Right? Simple. All right, cool. So that served us really well from 2012 to 2015. We started running into a lot of issues with Google App Engine, not the least of which that some of our just depth 1 queries would take like 20 seconds to respond. So around 2015, for a lot of reasons, we made the call to migrate off of App Engine altogether. And also the sort of Silicon Valley story of we're not going to do monolith anymore. We're going to do a bunch of microservices. And so we were sort of casting around for a data store. None of us had any real experience with PostgreSQL or MySQL. I remember reading a bunch of documentation and saying, wow, PostgreSQL seems to have some really good JSON support. And that was pretty much, we were moving really fast. That was pretty much the extent of our evaluation. So we had to figure out how to store trees in relational databases. And I did a fair amount of reading at the time, and there's some sort of 4 kind of common patterns that you see. Probably the most simple is you just store a reference to a child's parent on the child. This is super easy. I've got a couple queries here. If you want to get all the children of ND001, you just select all the rows that have that set as the parent. And you can kind of just recursively go down the whole tree that way. Super simple. Has some issues. If you care about the order of children, you need to find another way to encode it. You don't get that naturally through these queries. The parent has no intrinsic understanding of who its children are. And this was not going to work for us for a host of reasons. Another common way is Ancestor Array. And the interesting thing about all these approaches that you see a lot in the wild is that they're really all just a refinement on the parent, setting a parent ID on the child. With an Ancestor Array, instead of just encoding the immediate parent of a child, you encode the entire path up to the root. And you do it with an array of unique identifiers. So here, in this example, we have the part and the ND that leads up to the root of the tree. That identifies the parents of this lesson or the ancestor tree of this lesson. This is pretty cool. You can do, it's a lot easier to reason about what tree a node is in if you have the entire ancestor path on each row. Issues with this approach, Again, you don't have a built-in ordering for children. You need to encode it somewhere else in your data. And also, moving subtrees around becomes very difficult because now, since the entire ancestry is encoded into every node, if you want to move a subtree, you have to recurse the entire tree and update that ancestry on every node. So the next thing you see a lot is materialized paths. And we've actually used this some. And this is basically just encoding the ancestor array into a string that is a little more application domain friendly. Everybody understands paths. There are libraries for parsing them. The big problem with this, it has the same drawbacks as ancestor arrays. The other issue is now you have this opaque string in your database. Postgres doesn't know anything about this. It's just a string. You can do cool string op type queries. Makes it easy to get everything below a node. But there's a much better way. And if you're ever considering this, this is a really cool extension to PostgreSQL specific. It's L-tree. And so you can take your materialized path, use the L-tree type, which is an included extension, use the L-tree path syntax, and you get a whole bunch of it's no longer opaque to Postgres what your path is. Thanks to the L-tree extension, you can actually do tree native operations like here we do containment. If you're familiar with the containment operator from JSON, you can do it with paths as well. There's also a very robust sort of query language, DSL, that you can use inside the query string to sort of say, partial path matches on individual path components and whatnot. And one of the really cool things that you get with this is that it becomes really easy to move trees around because you have a bunch of operators. Here, you can just pop off the top of the path and then append the new parent to it, or prepend the new parent to it, only for nodes that are contained in that path. So this is super powerful. Ultimately, we didn't go with any of these solutions. One more thing. There's a really, really good blog series on L-tree from Pat Shaughnessy, and I put the link up here. So ultimately, what we went with, I just showed you all these different ways of doing it. We went with basically what we had in Data. We encode the children and the parent. And the big reason here is it's super important that our parent nodes know the order of their children. I mean, you think about our content. We don't want to be teaching about pointers before we've talked about identifiers. It's super important that pedagogical content is in order. And we didn't want to deal with the complexity of encoding that order elsewhere. So we've got this really simple data model. Caused a lot of problems in the long run, but since we were migrating from an existing model, it made the transfer from Google App Engine Data Store to Postgres much easier. And so this is what this table, a simplified version of this table, looks like. We derived a unique identifier based on some properties of the content. We still have our keys. Now the children array, which is a native PostgreSQL array with ints, semantic type, which we talked about earlier, and our JSON data blob. And here I've just modeled this all the way down to the atom level. So this slide was supposed to be deleted. So problems with this approach. Actually, this worked really well out of the gate. Our query time went down. We were using with recursive. I did an awful lot of with recursive querying for a year. But compared to what was happening in Data Store, we were able to deliver content to students on the order of milliseconds instead of seconds, which was a huge win for us. But over the course of 2017, some of the choices that we made with that kind of simple data model with the array of ints as the children started to bite us, especially as we scaled, not just in terms of the number of students, but in terms of the number of people creating content, which exploded in 2017. So one of the big problems, and to be clear, these problems are fundamental to the data structure choice that we made. And that's one of the reasons I want to call them out. Like these things have real impact. And if you can see around corners, well, if I can help anybody see around corners, I'll consider this talk a win. So one of the big problems was that if you look at that data structure, if you make a change to a node, you've made the change. It's an update, right? So it's mutable in that sense. We have good tools to help people sort of keep their development away from students until they're ready to launch. But once they launched, any change to the content, a typo, would immediately propagate. You make a change in our content editing tool, and the next student that asked for that content would see the change. This seemed like a feature at first. But as we scaled up to more content creators, what we found, and when we started entering new markets, we went international, what we found is that a lot of people started reusing content, which makes sense. We don't want to like create a new GitHub course every time we do a programming nano degree. So people would start linking in their children array, effectively, they would link to an existing bit of content from another nano degree in this case, let's say. And what would happen is they would think they had a copy or just not think about it at all and go, oh, this is cool. I reused this content, but I don't need these children. And they would delete it. But immediately, everybody over in this other nano degree, all these students, their content disappears. This started happening almost on a weekly basis. And versioning. Again, these changes are made in place. The only information we had was sort of the time of the last change and who did it. There's no sort of like audit log or history of changes to content. And all these three things tend to exacerbate each other. If people are sharing nodes and mutating them and everything goes out instantly to students, it's a huge problem. When these things happen, if you don't have versioning, it becomes really scary to get them back in a previous state. Situations where my colleagues and I are, shelled into a production database serving millions of students in real time, hoping that we get the update statement right to sort of undo a problem. So these are the problems that motivated our, this is a quote from one of our content developers that sort of made my blood run cold when he said it. And so I put to you, there's sort of a fundamental running thread through those three big problems that we encountered. And that problem is that our content was mutable. And so I'm going to go on a bit of a rant here. I'm almost smart enough to not show up at a relational database conference and say that CRUD is bad, but I'm going to say it. What I've seen with developers over the last few years is that they tend to default to CRUD. Start a new app, fire up your ORM. This is right there, update and delete, right? And they start doing structural updates and deletes instead of kind of logical updates and deletes. And this kind of mutability, it's interesting because in programming languages, there's a lot of noise around mutability is bad. A lot of good press for immutable data structures. But a lot of the people, sort of working on that stuff, first thing they do, they get a database and they start, writing SQL for update and delete. So I've been counseling folks to sort of focus on append systems instead of append and retrieve, and to sort of leave the update and delete, at least to sort of bias towards that. I think right now there's an over bias towards update and delete, like at the row level. And I really want to counsel sort of app developers and system designers to think about where they can do that logically. If we had done this early on, it would have saved us a lot of grief. There's a really, really good talk on this from Martin Kleppmann called Turning the Database Inside Out, which I can't recommend highly enough. All right, cool. So we got through our motivation and a little bit of a rant on CRUD. Let's talk about the design of our new system. And so if mutability is the problem, probably the first thing you want is immutability. And the other thing that we were really interested in, and these things sort of go hand in hand, is making everything content addressable. So if I store a series of bytes in our content store, I should get some kind of immutable reference to that exact sequence of bytes. And a great way to do this is with digests, right? So you send me a bunch of JSON. I put that JSON in a stable format. I take a digest of that JSON. I give you back the digest. From there on out, forever, eternity, if you give me back that digest, I will give you your JSON bytes. And so that was sort of the fundamental idea. It goes deeper than that. There's kind of a subtle implication that if you put the references, earlier we talked about how you should store your kind of tree structure separately from your data. So we have the children array right from the outset. But actually, that's a mistake because the references to other documents in your store are actually part of the content itself. And if you're going to version, if you're going to version your content, you're definitely going to want to have those relationships be versioned with it. So once you do that, if you have a SHA to a node and its links to children change, its SHA will change. And that goes all the way down the tree. Does this make sense? So you always have, by having a stable reference digest of a node, you can actually reason about the state of not just that node, but every descendant. And these are called Merkletags. They're also called Merkle trees, but I think Merkledag is a lot more fun. Try it, Merkledag. Come on, guys. Merkledag. I know it's after lunch and everybody's lethargic, but Merkledag. Look at everybody who actually said it has a huge smile on their face right now because it's fun to say. But in any case, this is how Git works, right? So we have content digest all the way down the tree. We only need the top level SHA to know everything there is to know about the state of that tree all the way down to children. So this was our new table. Of course, I always strive for simplicity. I think we're getting to like a sort of a lower bound of simplicity here, but it's a 2-column table. It only has a SHA column and a JSON-B column. You give our store any JSON, we'll put it into a stable representation, give you back the SHA for that. From that point on, you can call getNode with the SHA, and you'll get your node back. And here I've sort of illustrated, I've illustrated that we have, instead of children, we have objects in a links property. And I'll get more into that in a second. But here you can see that we're storing a SHA, a link of type SHA with the value that is also a SHA. And you can reason about how that would go all the way down the tree and give you a completely immutable reference to the state of that tree at any given time. So this is going to start looking a lot like Git. The next table we have is commits, and this is super simple. Basically, we're just storing all the changes to a logical entity. Applications define what they care about versioning, at what level they care about versioning. But we just store the author, a timestamp, the SHA, and a unique commit ID. And if this is part of a series of changes, we store the parent ID. And again, anybody familiar with Git internals is not going to be surprised by this. Cool thing about this is a simple self-join will give you a commit history. And then refs and tags are what we use to sort of map application domain identifiers to these commit IDs, because nobody really wants to be holding on to commit IDs in their applications. So this is an arbitrary string. The only difference between refs and tags is that refs are mutable and tags are immutable. And so that's it. That's our entire sort of base content store. And from these primitives, we've been able to build very sophisticated applications, things like branching. We don't have the tooling yet to do merging, but it's really just a function of figuring that out. The data store supports it. I wanted to get into the links a little deeper. So because we have a bunch of applications that are used to this behavior of a reference to a child, kind of following the head of that child, the latest version. We also support ref and tag links. And we have to be careful with these because if we're not, they'll exhibit the same problems we had when we just had sort of an opaque reference to an application identifier. But this works because in a lot of cases, people, content developers, do want the links in their document to just point to the latest of something. So they can give it a name. And as those refs are updated, they'll always get the latest version of the content. Does all this make sense? Any questions? Pretty simple. OK. So let's take a look at how this addressed our problem specifically. So the first problem we were trying to address is this issue where save and publish are the same thing. If I make a change, it immediately goes out to students. With the new model, it's actually very simple to just take a snapshot. And when you take a snapshot, you just traverse an entire tree and convert any dynamic references, any ref links into SHAs. And at that point, that snapshot is locked forever. You store that snapshot at a new tag. And then when students request content, when the classroom requests content, it always requests a version, a tag ID, basically, along with whatever it is the student wants to see. So we only look in that tree for the lesson or concept or whatever the student is looking at. Shared nodes, people stomping on each other. So we had to build tooling to make this work. The data model changes didn't solve it alone, but the data model changes gave us the ability to branch. So if somebody wants to reuse, say, the GitHub course, they can do that, and they can use it dynamically, just like they did before. But if they want to make changes, they just branch. They just branch, and they can start making changes. They can delete children, and it's not going to impact anybody else. The only thing we have to be careful of is that when they branch, we actually have to update any dynamic refs in the descendant tree to ensure that they don't have a clone of the sort of top 3 levels, but make a change to something 4 levels deep that other people still have references to. But that's a straightforward problem to solve. Wow, I just talked through this whole slide without pulling it up. All right, versioning. Versioning is pretty obvious. We have a lot of primitives now to sort of build higher order versioning functionality for our customers in the sense that we can use the commit history, which is super value. Snapshots and tags are also very valuable. Anybody can sort of take a snapshot of a tree. So we've built some cool tooling to let the sort of content teams be able to say, OK, this is the version we want students to see. And obviously, during development, they can just roll back using the commit history. So we solved that. That's weird. All right. So the third part of this talk is stuff, which is kind of a catch-all. We learned some things that were surprising for us, maybe not surprising to anybody in this room, but when we were working with PostgreSQL, we're all sort of application and system developers, and a database is sort of this place where you dump your data, right? The surprising thing we learned, the theme through all of these is just go ahead and do it in PostgreSQL. It just works. And so the really surprising thing to me was I started prototyping our new content service using database functions, PLPG SQL, or SQL when they were simple. And at first, I was just doing this sort of as a proof of concept. And what I found is, by modeling it this way, we wound up with these wonderful, in the database primitives. And then when we did go to write our service, we weren't writing these elaborate and maintaining these elaborate SQL queries in the database. I'm sorry, in the Go source. We were instead just calling these simple primitives in the database. This was super surprising to me. I would have never expected this to make it to production. But it's worked really well for us. I think my remote stud. And so here's another example of the put node function, which is really straightforward. So most of our content service is actually Postgres code now. The Go code is mostly a gRPC boilerplate. And so when you make this big of a change to your data, there's the schema migration itself, but there's also this issue of, like, you have this system that's working. It's serving millions of students, 1,000 content developers. How do we kind of switch it out from under them? And I mean, this was like the hardest part of the whole thing. And this is what I felt like the whole time. And I actually did feel like later I was running away from the giant ball that was coming down the cave. Everybody knows what this is, right? All right, cool. So a technique that I'd learned at another company for distributed systems for this sort of thing, for standing up new services and then kind of safely and in a low-risk way migrating all of your traffic over to it without bringing the entire site down, is this idea of dark writes. Is everybody familiar with dark writes? Cool. So in a distributed system, a dark write setup might look like this. We have our legacy system. We have clients making requests and responses, and we have our new system. And right now, it's not taking any traffic. It's just stood up in our Kubernetes environment. It's not doing anything, but it's passing health checks, hopefully. So the first thing you'd do is you'd put a proxy between the clients and the legacy system. And it doesn't actually have to be, this is more of a logical proxy. Oftentimes you do use an actual proxy, but it could just be that you write some code in the legacy system that is going to take care of the next bit of this. But I found proxies to be the lowest risk way to do it that gives you the most visibility. So now all your traffic is going through this proxy and to the legacy system. Clients don't know any different. Legacy system doesn't know any different. And then in the proxy, you start duplicating requests and sending them to the new system. And this is the dark part of it, right? You're sending live traffic to your system, but you're not using that system to respond to requests. So the legacy system still handles the request. The proxy routes that back to the client. Meanwhile, the new system takes the write. And typically, you'll have another system sort of checking consistency between the legacy system and the new system. And again, that could be logical, or it could just be literally another service that's running that's doing those checks. If your new system is something that responds to users, another great thing you can do here is we call them dark reads. And with dark reads, basically you take the response from the new system, transform it into whatever back-compatible version you're going to give to the clients once you flip the switch, and then compare that to what you expected, and then just log it, monitor it for failure. I've done this a lot. It saved me a lot of trouble, although it is a fair amount of upfront work, but it mitigates risk almost completely. If something goes wrong, you just take your new system offline, fix it, try again. The other great thing about this is that after you flip the switch, the legacy system keeps taking writes. So now the legacy system is getting dark writes. If something goes horribly wrong with the new system that you didn't detect during its dark write phase, you can just flip the switch back. The systems are still consistent until you elect to take the legacy system offline. Done that a few times, and boy, that'll save you. So this is a really powerful model, and I was all ready to apply it in this case. And then this kind of mantra of do it in PostgreSQL came back to me. Those slides were supposed to be hidden. I don't know what happened. Came back to me, and I started thinking about, could I do dark writes without building all this infrastructure? And sure enough, instead of writing a couple Go services, we just wrote a page of PLPG-SQL. And what this basically does is everything you get from dark writes, but it just does it with a trigger. So when a write comes into the old table, the new nodes table, we transform it into the new, all the appropriate entries in the new content model, and we stuff it into those tables. And then there is a very small Go service that checks consistency and wakes me up at 2 in the morning if anything goes wrong. This was incredibly powerful. Like dark writes, the dark writes model itself, but doing it in the database, this was so much easier. And it really increased our confidence as we got ready to ship this. And then one thing I didn't mention when we were talking about dark writes in a distributed setting is that once you've got the consistency and you're ready to cut over, you still have to get all the data from the original, the legacy system, into your new system. And this can be a pain. You spin up Kafka, depending on what you're doing. You spin up a queue system, you get all those messages in. That almost never goes right the first 3 times. So that's a painful, stressful, long process. By doing our dark writes in Postgres, once we were confident about consistency and that writes were consistent and we weren't going to have any issues, this is literally our ingest pipeline. So by doing a no-op update on every row in the old table, we triggered an insert into the new table, or tables. And from that point on, we were 100% consistent between the old system and the new system, and we could conceivably just switch our systems over at that point. This insight, again, from somebody who doesn't have a strong relational database background, this is incredibly powerful because this would have been like 3 weeks of work for me at other companies to sort of ingest all this data over the network and check it for consistency. So that was huge for us. There's another thing that we just recently discovered, which is we sort of treat the JSON as opaque for our applications. You stored some JSON, here's your SHA. You want an application domain identifier, create a ref for a tag, but that's your JSON, it's your problem. Because we thought performance would be a problem. We just released the ability to find nodes within a tree by matching the JSON payload. And we just did that with the JSONB contains operator. And that is super fast, especially when you're constraining to a tree of maybe 6,000 nodes. That is incredibly fast. You put an index on that column, and it's worked really well. And our users are super happy because now they can build more robust systems. They don't have to maintain a bunch of refs just to find the node they're looking for. And so this is, again, the mantra of do it in PostgreSQL. We couldn't be happier. And if I were to rename this talk, it would probably be something like, Postgres is already a scalable document store. We just added versioning. So that's all I have today. We sort of talked about our motivation for doing this, the problems that confronted us at Udacity, which are kind of unique to our problem. The design, basically Git on top of Postgres. And a couple of things that I thought were really interesting as we went through the process that were specific to PostgreSQL. And that's it for me. Thank you a lot. Oh, one more thing. So when I ran this deck past my daughter, when I rehearsed the talk, she's like, her only feedback was more emoji. So that's why there's as much emoji as there is. You guys have been great. Any questions? Yeah.
Can you talk about your data volume increase from the old version to the new version, or you're updating versus kind of asset?
So it's not anything I think people here would sneeze at. We have about 8,000 JSON documents. Or, I'm sorry, 800,000 JSON documents, and we're very read heavy. This is something else that we're working on. It's really not a problem with this new model, but I can see it being a problem in the future. But with snapshots, we can basically we can cache things at the edge now. We can put the JSON outside the database and have people access it directly. But yeah, our data volume, because we have about 1,000, at any given time we have about, I would say, 1,000 people creating content. That's just not a problem. And I was really surprised that we were running into the query. I think a lot of our issues on data store were self-inflicted. But we definitely, we spent some time trying to optimize it, and we were having a lot of trouble doing depth end traversals in a reasonable amount of time. But yeah, I don't think, I used to work at Google, the kind of volume we have is not worth mentioning. Does that answer your question? Or I'm sorry, and you know what, I forgot to repeat the question. The question was, could I give a little more detail about the volume that we see? And then I sort of, sheepishly said we don't really have much. Other questions? Oh yeah, sorry. Go ahead.
So I was curious, as far as the content, whether it's written or text content or video content, how are y'all storing
The video content, we have a whole nother pipeline for video, and we store it in several places. For US and Europe, and I believe India, we just send it to YouTube, and that's where people watch it. For China, we have other solutions, and for mobile, we actually do host a pretty large video storage service just to serve the videos to mobile. Everything else, at least its metadata, at the very least, is stored in this store. And actually, another cool, I designed the system to work this way, but it's been surprising how quick the uptake has been. I was trying to build a generic store that people could use for other applications. You know, if it didn't make sense for them to have their own, one of those 144 RDS instances, that they could just start storing data. And that's gone. We had people going to like Contentful, like using outside vendors for sort of JSON stores, and we've already had a couple apps adopt this, so that's pretty exciting. But yeah, video is processed in-house by a sort of encoding pipeline, and then shipped out to wherever it's hosted.
What about like photos?
Photos are similar to video. We host. It's all in an S3 bucket, basically.
Yeah, that's why we run into is that like consistently you hear that you shouldn't store large binary data in Postgres.
Yeah, we definitely don't. Yeah.
There are definitely lots of arguments. Mm-hmm. It's like, oh, we've never tried it, so it's like, well, that's the worst could happen.
One thing that we've been experimenting with is hashing large binary content to help with versioning. That's actually, that's one of the shortcomings of the system today is that it doesn't really, videos we can do, images right now there are upstream, or I guess downstream considerations that make it possible to version images, but the system right now is not automatically hashing those. So, but yeah, we don't store large binary objects in Postgres. Any other questions? Because I went short. All right, go ahead.
It looks like you're storing all of your hashes as strings.
Mm-hmm.
Did you think about binary, like micro-representations?
That's a good question. I wonder if that's going to bite us. No pun intended. But at the time, it made sense. We'd been using UUIDs elsewhere, and we hadn't seen any problems. But it keeps me up at night a little bit, wondering if it would not be, the thing I sort of tell myself is that it wouldn't be too bad to migrate this to byte A and provide a sort of transform at the application level.
I think just to comment on that, like the big thing you can see is that by using, if you store that data as like base 64, you have like 40% data increase in size, and you have 100% increase in size if you use like X. And it's also true that indexes are a lot slower to maintain because you probably have UTF-8 on your text files to manage that UTF-8 data. But you can change the correlation on like one particular index and make that dramatically faster index.
Yeah, that was another. I mean, the point you brought up about 20 bytes versus 40 bytes. I'll repeat the original question in the comment. The question was, I see you're using strings for SHA. Did you consider byte implementations? And we didn't really consider. We thought about it briefly, and then we just went ahead and because of the UUID. And in the comment, it's a good one, is that you want to be careful that your indexes aren't UTF-8 if you are using strings as a primary key with the sort of random string like that. And this is all stuff that is sort of still evolving for us. We tend to put out the fires, and we don't always have time to anticipate the next one that's going to come up. But yeah, our sort of answer to that was just we'll probably switch. Yeah, are we going to get to like 100 million rows anytime soon? Probably not. But if we do start seeing that that's a performance bottleneck, then well, that's a good point. Thanks. Sure.
Is there a limit, like in terms of like you define, you're storing a tree inside Postgres, so is there a limit number of children that you can store? Did you notice anything specific to that?
In terms of depth or in terms of cardinality or like? Yeah. So the question was, have we noticed any issues with the number of children in terms of cardinality? And to date, no. That tends to be in the teens to 20s. So I'm not sure there's no restriction on it, at either the database or app level. So I don't know. Get back to me. I'm not. I mean, what were you gonna say? Oh, I think because I don't see it being a problem, because you can think of the children of a given node, right? There may only be like 8, but there could be 3,000 child nodes altogether, and we fetch that entire tree all the time. And so my hypothesis is, if we had 3,000 children at one level, it wouldn't be any worse than that recursive descent down the whole tree. But that's a hypothesis at this point.
Because most relational databases are stored as trees in some way.
Right.
Because it's like foreign keys and then foreign keys.
Mm-hmm. Mm-hmm.
So that's why, the reason I ask is there's no limit there, but essentially the limitation is how much time you want to spend fetching the next set of children.
Right. And I expect at some point in the, hopefully this time it's more like 3 to 5 years instead of 18 months. We'll have to look at the performance there. And on that note, there's sort of a fair question: why not just use Git? Why not build GitHub for content? But the backing store is still basically Git. And we actually had some long conversations about that, and that still might be what happens at some point. And clearly that scales, or at least it did for GitHub. So yeah, did that answer your question, or? Okay, cool. Any other questions? All right, you guys have been awesome. Thank you.